All right, welcome again. So in this lecture, we're going to review the master theorem, which helps you to find the complexity of a recursive algorithm. So let's say, for example, you have an algorithm that divides a problem into smaller subproblems, and then it combines them together to get the solution for the original problem, such as merge sort. We reviewed in the one of the previous lectures that merge sort would divide an array into two subarrays, and every subarray will also be divided into two subarrays, and so on. Okay? And every time it solves a subproblem, it merges the subarray and another subarray, and then it combines them together to get solution for one of its subarrays. Okay? And it keeps doing that recursively. So what is the complexity of this idea? We can write any divide and conquer algorithm as following, with a recurrence relation. So let's say the algorithm is called T, okay? So that we're talking in general, not about merge sort specifically. So an algorithm T of size n could be written as A times T of n divided by b plus n to the power of k. Okay? It could be more complicated than this, but most of the algorithms you're gonna deal with could be written like this. Okay? So what is the a, and what is the b, and what is the k? Basically a is the number of subproblems for every call. We know that if we have an array, that array will be divided into two subproblems. So we would have two other arrays, two calls, two recursive calls, okay? So this algorithm is order 2. It means that it makes the first call and then it makes the second call, okay? So this algorithm has A equals 2 because it makes two subproblems. If it were making three recursive calls, then A would be 3. Okay, so A is the number of subproblems, the number of recursive calls. The B, however, or let's say the n divided by b, is the sizes of those subproblems. So every time we're taking a problem of size n, and then we're creating a bunch of subproblems, every one of them of size n divided by b. Okay? And for the n to the k, or it could be any complexity, basically, that's O of something, that's the complexity of merging or combining the subproblems together. So we make the division, we divide problems into smaller subproblems, and when we combine them together, we combine them with some algorithm that has complexity n to the k. Okay? So for the merge sort algorithm, the merge sort, so the merge sort of n equals 2 times the merge sort of n divided by 2 plus n to the power of 1. It means that the merge sort algorithm, whenever it gets an array of size n, it creates two subarrays, every one of them of size n divided by 2, whatever the size of n divided by 2. Okay? And after that successive division, it will combine the result. In our example, it'll merge the two arrays with an algorithm that has order n. Okay? It has order n. So basically, if we take a look at the merge sort code here that we've seen in the previous lecture, this is the merge sort function. So this is the merge sort function. We have here a constant operation, and this is also another constant operation. And here we have the first a call for the first subproblem, a call for the second subproblem, and this is merging them. So merging them is, the complexity of merging them is O merge of n. Okay, so the complexity of merging them is whatever the complexity of the merging algorithm, and we're going to see that in a moment. And we're going to prove that the complexity of that algorithm merging is order n. Okay, so we said that we have two subproblems. For that reason, a equals 2. Okay, and the size of every subproblem is half, because for the first subproblem we're taken from the beginning up to m. So that's half from the beginning up to end, okay? And then we have from m plus 1 up to end. That's also half, okay? So the size of this problem is the size of the original problem divided by 2, and the size of this problem is the size of the original problem also divided by 2, okay? And for the merge algorithm, we have here a bunch of constant operations here, and we have here a while loop. So this while starts at most from the beginning to the middle, okay? And the j starts from the middle to the end. So at least here we have n divided by 2 operations, and basically here we have also n divided by 2 operations. And the overall here, as you can see, when I gets incremented, j is not incremented. When j is incremented, then I is not incremented. So basically, this is n divided by 2, this is n divided by 2, so the sum of them is n, okay? Because let's look at it in a different way. So every time we're adding an element to the temp array, and the maximum number of elements that we're going to add to the temp array is n elements, the size of the original array elements. We're just going to copy them all. Whether we copied them all inside this while loop, or we copied not all of them using this while loop, and we copied the rest using the other while loops, the overall operations would be n. And of course here we're going to copy them back, so that's also another order n. So we have here order 1 plus order 1. Sorry, order 1, so this is order 1 plus this one is order n. This whole one is order n. And then we have another order n, so that's plus order n, okay? So whenever we have two complexities that are both linear, then we can take the maximum one, or you can look at it differently. So this equals the complexity of 1 plus n plus n, which equals to the complexity of 1 plus 2n. So here we take the linear complexity, because this one is very small that we can not consider it. So that equals to the complexity of order 2n. And the 2, since it is constant, we can take it away. So that's order n, okay? Because for very large n, that 2 is really, it's not going to change a thing, okay? This is just like as the limit. Whenever we take the limit, we deal with the ones, the elements with the higher degrees, okay? So the smaller ones will not make a very big change as if n approaches infinity. Anyway, so this whole algorithm is order n, okay? So k equals 1, because the combining algorithm, we said that t of n equals 2 times t of n divided by 2 plus n to the k. So the combining algorithm is n to the 1, so k equals 1, okay? So that's equals 1 in the merge sort example, and a equals 2 and b equals 2. So let's get back to our sheet there. So here we have the merge sort of n equals 2 times merge sort of n divided by 2 plus n to the 1. So to determine the complexity of this, here's the statement of the master theorem. So the master theorem says that if we have a is bigger than, let's say it's bigger than b to the power of k. In that case, the complexity of the algorithm t would equals to the complexity of n to the power of log of base b of a. Okay, so this is the complexity. If a equals b to the k, then the complexity of the algorithm t equals order n times k, n to the k, sorry, times log of b of n. If a is less than b to the k, then the complexity of t, of the algorithm t, would equal to order n. Let's remove that. Let's take that away. So equals order n to the power of k. So these are the three possibilities that you have to remember. You have to always remember. I suggest that you write these in your notes, because you're going to always use them whenever you have a divide and conquer recurrence relationship of a recursive function. Okay, so let's apply these this theorem in our example. So we said that merge sort of n equals 2 times merge sort of n divided by 2 plus n. Okay, so a is 2, so let's write that down. A is 2, so that's 2. And we have b to the power of k, b is 2, k is 1, so 2 to the power of 1, that's 2. So let's compare 2 and 2. 2 equals to 2, right? So we are in this second scenario. Okay? So the complexity of our function would be order n to the k times log b of n. So let's write that. So the complexity of our merge sort algorithm, so let's write that. So our merge sort algorithm equals order n to the power of k, k equals 1, so that's n to the power of 1, times log of b, that's base 2, so log 2 of n. Okay, so and that's basically true. The complexity of the merge sort is n log n. Okay, log n log 2 of n. Okay. So here's another example. Let's give you another example to make sure that you got the idea right. Let's say you have an algorithm called t of size n. Okay, and that problem will always generate, let's say for example, 3 t of n divided by 2 plus n squared. Okay, let's say you have some algorithm that for every problem it divides the problem into 3 subproblems. It makes 3 recursive calls, and whenever it combines the subproblems, it uses an algorithm that has complexity n squared. Now, what is the overall complexity of this recursive algorithm? Well, we just apply the theorem. So we have a equals 3, so a equals 3, b equals 2, k equals 2, okay? So k equals 2. So b to the power of k equals b to the power of 2, so that's 4. Okay, so we have a equals 3, b to the power of k is equals 4, so it's less. 3 is less than 4. Okay, so here we are in this scenario. A is less than p to the power of k, so the complexity of the algorithm t of n equals order n to the power of k. In our case, k is 2, so it equals 2n squared. Okay? Let's see another example. Let's say that we have t t to the power of n, let's say t to the power of n equals 8t to the power of n divided by 2 plus n. Okay? Let's say you have an algorithm that has this recurrence relation. So basically we have a equals 8, b equals 2, and k equals 1. So let's write that. So we have a equals 8, we have b equals 2, and we have k equals 1. So b to the power of k equals 2 to the power of k, which is 2 to the power of 1, so that's 2. We have 8 is bigger than 2. So basically, the complexity of t of size n equals the first complexity here. Okay? So that's order n to the power of log b, log 2 of a. A is 8. So let's calculate that. So the log 2 of 8 is 3, so that's order n cubed. Okay? So basically these are a couple of examples for the master theorem and where you have to apply it in order to get the complexity. So basically if we review this, whenever you have an algorithm that divides the problem into smaller subproblems, the number of those subproblems is a, and the size of those subproblems is n divided by b, and then you combine those subproblems together with some algorithm that has complexity n to the power of k. Then basically if you have here a is bigger than b to the power of k, then the complexity of the algorithm is order n log b of a. If a equals b to the power of k, then the complexity is order n to the k times log b of n. If a is less than b to the k, then the complexity of the algorithm is order n to the power of k. And we have reviewed a couple of examples here, so I hope the idea is clear. If you have any question, feel free to raise a question. And that's it. See you in the next video.